Good evening. I'm Kaushik Bhattacharya, professor of mechanics and material science. I also currently serve as the vice provost at the Institute. It's my pleasure and privilege to welcome everyone here for this evening's Watson Lecture. We have you in person and also a whole group online. So a warm welcome to all of you. A special welcome to the students from the Garfield High School in Boyle Heights. We're glad that you could join us. Their visit is made possible with the support of the Friends of Beckman. This is a group which supports various activities, and in particular, activities and events that broaden the engagement and awareness of Caltech around this lecture series. We thank you for your support. This year marks the centennial year of the Watson Lecture. These series of lectures started about 100 years ago for the purpose of introducing and exposing the public to science, technology, engineering, and mathematics. And through annual talks by faculty across the Institute's research divisions, the tradition has continued, providing faculty with an opportunity to share the research with public and the local community. Our lecturer today is Chiara Daraio, Bradford Jones Professor of Mechanical Engineering and Applied Physics in the Division of Engineering and Applied Science. This division is a collaborative community of about 100 faculty working at the leading edges of fundamental science to invent the technologies of tomorrow. We address fundamental challenges or questions that are critical, the fundamental questions that form the critical roadblocks in addressing the biggest challenges, technological challenges facing humanities. Our speaker this evening exemplifies this. Her research studies fundamental questions in the mechanics and physics of materials and structures and uses the insights from these studies to develop new technologies in medicine and sustainability. She's a member of the Academic Council of Schmidt Futures and Rhodes Trust, as well as a member of the Board of Editors of Science. She's a Heritage Medical Research Institute investigator and was named among the Brilliant 10 by Popular Science. She's an entrepreneur and a much sought-after consultant in the technology industry, in addition to being a very active mother. Not only does she juggle all these many roles, she actually happens to be a juggler in real life. We'll begin with a short film about Chiara, after which she will deliver her lecture. The audience will have an opportunity to ask her questions after her talk.
I grew up in Ancona, which is a small town on the east coast of Italy. Even elementary school and middle school, I was very much into building and into inventing new things. And I think I got that probably from my grandfather, who was a very creative fidgeter in building all sorts of contraptions at home that were solving practical problems. And I was fascinated by that. However, mechanical engineering really was a choice of convenience at the beginning. I was the first one in my family to pursue an undergraduate education. So I picked effectively the major that was based in my hometown and that had the most physics available in the courses. My name is Chiara Daraio, and I'm the G. Bradford Jones Professor of Mechanical Engineering and Applied Physics in the division of ENS. As an undergraduate student in Italy, I became interested in expanding the horizon and exploring opportunities for study abroad. I jumped at the opportunity. I was excited to be in San Diego, California, and that's how the journey began. I'm very outdoorsy. I really love to be outside, and there were so many things you could do on the beach and the parks. And so I just decided to stay, and after my undergraduate thesis, to remain in grad school for a master's and PhD degree. Having a job at Caltech has been one of the luckiest and most fortunate opportunities in my life. We can have, brilliant ideas everywhere, But there are only unique places like Caltech where these ideas can then, flourish and mature into, through discoveries and eventually practical applications.
What came out, it's really, really good. Now it really feels...
The beginning of my career was focused on very fundamental questions that linked the structural properties of materials, the geometrical elements that are formed in the atomic structure all the way to the micro, meso, and macro scale. And today, this understanding of structure related to functionality, so why materials behave the way they do, why do they have certain properties, and how can we design those properties to fill the needs of specific applications, is something that is more and more driving my research towards solving societal problems at large. I think often teaching, even the same subject over the years, allows us to understand much more in depth some of those fundamental concepts. That is something that I have particularly appreciated at Caltech, because the students here are so inquisitive and so phenomenally smart that they helped throughout my career really ask those fundamental questions and get to the point of mastering the subjects that certainly wasn't there at the very beginning of my work here. After so many years of discoveries and publications and research in many different disciplines and areas, I find most satisfying the ability to see students and postdocs succeed in their own personal endeavors. I think in a way I live vicariously through their successes today by seeing, for example, when a postdoc nails the job of his dreams or her dreams. Vice versa, when students, for example, win awards and prizes for the research they've done, in a way allows me to live again and again and again the same excitement that I felt the day I received an offer from Caltech. And that's certainly something that gets me up in the morning.
Good evening, everybody. Envision a future where devices and the digital world become a seamless part of us, embedding sensors, actuators, microcomputers, and antennas in the very fabric of the clothing we wear. A future where you will no longer stare at the screen of your smartphone, but where clothing will be able to sense our well-being, monitor our metabolic activities, and intuitively extend our abilities to communicate, work, and pursue our hobbies. Clothes are getting smarter. Advances in material science, manufacturing, and computation are enabling a wearable revolution. But let's start from the very beginning. Archaeologists in Germany discovered the first evidence of use of clothing, suggesting that prehistoric animals were skinned for fur well 300,000 years ago. These clothing were probably consisting primarily of skins that were wrapped around the body without elaborate tailoring. This is because the discovery of eyed needles that are required to sew more intricate designs didn't emerge in the history of archaeological records until about 45,000 years ago. However, since then, we've been using clothing for temperature regulation, protection, and aesthetics, which are the primary reasons we're all wearing clothing tonight. The history of clothing and garments, however, have been inextricably linked to the discovery of new materials and new manufacturing methods. Humans evolved from using furs and skins all the way to developing synthetic polymers and textiles that have advanced functionalities. Let's think about the discovery of silk 5,000 years ago, or the creation of chainmail armors following the ability to forge iron and steel. Textiles also changed the course of history. For example, opening commercial routes between the East and the West, if you think about the Silk Road, or in helping the defeat of the Napoleonic army during the Russian winters, because legend says that the tin buttons and boot nails that were part of the Napoleonic clothing disintegrated in the cold weathers of Russia. Thousands of years took chemists and scientists to develop or try to recreate silk in laboratory that led us to the creation of something we wear today very often, like viscose and nylon, which they're now 75 years old and led to revolutions in how we dress and our apparel. The last 30 years or so have seen the rise of electronic textiles, or fabrics that embed electronic or conductive elements, or even lights in the form of LEDs, that can add functionalities to the clothing. So what is the future holding? Today, if you think about smart wearables, we can group smart wearables into two families. One you're probably very familiar with are electronic wearable devices, like smartwatches or phones, which we use today, for example, to monitor sleep, calories intake, and in some cases even monitor our mood. Perhaps you're less familiar with electronic textiles or e-textiles, also called smart clothing in some literature, which are starting to commercially become available. Let me give you some examples. Shirts, like the one you see here, that have embedded heart rate monitors, heated gloves that are incredibly useful in these cold snaps of the Pasadena winters. And to monitor running performance, you can also wear smart socks that, for example, monitor your steps and pressure under the foot. From specialized uses, like in high-performance athletics and the military, smart wearables are conquering larger chunks of the market and a broader commercial audience. For example, in sportswear, workwear, medical support, portable energy systems, assistance and communications, the market that's shown in the diagram here on the left is growing in the hundreds of millions for both projected between 2022 and 2032, projected between electronic textiles and wearable devices. The ultimate goal of the science and engineering that's behind these smart wearables is to embed devices, sensors, actuators, computing systems, and batteries directly inside the wearable fabrics, not as external rigid component, creating all-day wearables with the lowest friction for adoption and the widest possible use. However, to get there are certainly challenges in realizing such a vision. Smart wearables require the integration of multiple materials and components at different scale. One of the hardest things for smart wearables is that they have to interface with the human body, which evidently is soft and moves and changes with days and years. And interfacing with multiple materials also requires systems to become manufacturable at low cost and durable. Every time we think about using, for example, in harsh environment or washing clothing in harsh environment, requires this additional functionality to survive complicated systems. So one solution that's commonly implemented, at least today in electronic textiles, is to use regular fabric substrates and then integrate conductors or active elements in the fabrics by weaving, knitting, or embroidering additional components. However, this approach is limited in the applications because they tend to short circuit, they tend to rust when we wash them, and there is mechanical degradation due to the fact that, for example, the natural fibers like cotton and wool tend to absorb moisture, which is a clear enemy of electronic systems. Powering and electronic components are also a major hurdle. Solution to these problems require thinking outside the box, avoiding the conventional electronic devices solutions, for example, by simply miniaturizing what we do in silicon in your cell phone, and designing completely new materials with embedded functionalities like we've never seen before. My own research group at Caltech has been working on creating new materials for wearables over the last several years. But we tackled the problem asking basic science questions rather than creating engineering solutions per se. For example, we asked questions like, how can we create new molecular compounds that can work as record-breaking sensors that don't need complex electronic support or components? Or another question could be, how can we embed or engineer the structure of materials to embed new functionalities and properties that can augment the communication between humans and electronic systems, or that can provide on command, for example, mechanical support and protection? So the rest of this talk, will be focused on showing you 3 examples of how we pursue the creation of these new materials for wearable, which can be embedded in future wearable technology and can provide new functionalities and abilities to our clothing that perhaps you haven't thought about before. The first example I want to talk to you about has to do with materials that respond to temperature changes. And they respond by temperature by changing their own conductivity. Temperature, if you think about it, is an important biomarker that allows us to have early detection of a number of medical conditions, from hypo and hyperthermia, heat strokes, infections and inflammations, even fertility or metabolic activity. This project, though, started from a serendipitous discovery in the plants universe. As it turns out, plants also need to measure temperature on a regular basis because they regulate, through temperature measurements, they regulate the water intake, they decide when to shed leaves or decide when and where to sprout new leaves and branches. We learned this when we stumbled on an old paper that was published in the 1960s. This paper was written by a group of Canadian botanists that became interested back then in understanding the plant's abilities to respond to temperature variations. By planting nails on the branches and stems of a tree, they were able to demonstrate that conductivity in the tree was continuously changing as a function of the outside temperature. What that meant is that, for example, both on long correlation times, for example, in the diurnal cycles, so over days or months, they could measure temperature variations. But the conductivity was also changing, for example, when a person, which is radiating heat from their body, was walking by a tree. And it turns out that this is not just a property of the maple trees that the botanists were studying, but it's the properties of all plants and all living trees. That means plants can detect, for example, they're so sensitive to temperature changes, they can detect the presence of a bird on the nest, or the passage of people around them, or sources of heat where they grow. Botanists discovered this correlation between temperature and conductivity in plants, but did not explain at the time what caused the temperature sensitivity in plants. They suspected it had to do with ionic conductivity, but did not explain exactly what molecules or what mechanisms were able to support this. So we became very intrigued in understanding these observations and wanted to know more. We launched into an investigation that took a good part of several years, maybe 5 or 6, to discover that the molecules in the plant cell walls that was so responsible to temperature changes was a molecule that's well known in the food industry, and that's pectin. In order to do this, we decomposed the plant cell walls one molecule at a time, testing which one was responsible for temperature sensitivity, and discovered that pectin, which is a sugar molecule, which many of you may be familiar with if you're into cooking, or making jam or marmalade, is actually phenomenally sensitive to temperature changes. In the graph you see here on the right, let me see if I can get the pointer, there you go. You can see the response of pectin in the red, and compare, this is a response basically that we measured by measuring the changes in conductivity in a film of pectin over a temperature range of about 45 degrees Celsius. This is a relevant temperature range for biological matter, plants, or even humans, and compare the response, the changing in conductivity, to other materials that are found in the literature or used commercially for temperature measurements, showing that pectin itself as a natural molecule is 300 times better than the best temperature sensors available in the literature today. This was a phenomenal discovery to us. We were very excited about this, and it was almost incredible. So in order to convince you that this was in fact the correct discovery, I'm going to throw out a challenge to all of you and ask you to try it yourself, and especially for the high school student in the audience. I strongly recommend this because it's a great dinner trick that always impresses all guests. So you can try it because it turns out that pectin is very common in many fruits, dried fruits, for example. Turns out mango, which is depicted here, we're not supported by Trader Joe's, so this is not a commercial. Just whatever we found on the internet. So it turns out that mango, or whichever store you prefer to buy it, is very rich in pectin. Dried fruit works, however, in any forms and shapes. So you can use tomatoes, bananas, apples, whichever apple fruit, whatever you have in your kitchen. So here's what you need to do. You pick up a piece of dried fruit, and then you stick 2 electrodes on the piece of fruit. You see it here. And then I recommend grabbing one of those multimeters you have in your garage, always handy, and then just monitor temperature changes on the multimeter. You can do 2 things. You can move your hand, for example, close or far, just like when a person walks by a tree. Or like in the video you're going to see on the right, you're going to see a thermal camera image. In this case, it's going to be a video that shows precisely this piece of mango that in a temperature domain. So this is an infrared camera. That it's going to turn bright when it gets hot. And it gets hot because we're using a blow dryer to heat it up. So let's watch the video. Below, you start seeing the current readout from the multimeter. So you see that as the spike of temperature appears in the graph, you start seeing spikes in current appearing. This is something that I promise it's going to work in your kitchen. It's going to give you the most temperature-sensitive thermometer you've ever had. It's only going to last about a few minutes. And the reason why it's going to last a few minutes is that the mango and any other fruit in your kitchen is going to absorb humidity from your kitchen. And once water gets into the system, it shorts the ionic conductivity and the temperature response. And this responsivity falls, and the temperature measurements will not be possible anymore. So it works if you either encapsulate your mango or eat it very fast after your test, which is what happened in the lab most often. OK, so pectin. We talked about pectin, but I now convince you that pectin is the fundamental element that was responsible for the temperature sensitivity. Let me tell you just briefly about the molecular composition. Turns out that pectin is a very complex molecule. You see the chemical composition in this diagram, and the only thing I want you to take home from this is that it's a messy one. It has a long backbone chain with lots of side chains that we don't really know what they do. But the piece that's important to us is this backbone, which has 2 fundamental properties. One, it is the one responsible for pectin's electrical conductivity. And 2, is also the one responsible for linking with ions. And ions is what causes pectin to gel. And that's how you make jam, for example, or marmalade. So the key element is this chain in the middle. It's called the polygalacturonic acid. And remember, the most important piece is that it links with these ions that effectively glue it together to become gel. We use ions to make skin-like gels that are conductive and also have an amazing temperature response. In this image, you see, for example, a film of pectin that's held between 2 crocodile electrodes. Pectin is very transparent, so you don't really see the pectin, but you see it in the thermal image. This is the IR image of the same, and you see the little square, which is the film, the pectin film. What we did with these measurements, which is rather crude, is to compare the current increases in percentage in blue for the pectin between these 2 electrodes, and in red, the readout of the thermal camera. And you can see that there is a very nice parallel correlation between the 2, telling us that the readout from the simple pectin instrument is actually as good as one of the most expensive thermal cameras commercially available. Even in regions like you see here, where it almost seems like it's measurement noise, but in reality, the correlation persists if I zoom into this ellipse area to very high precision, making us think that pectin can detect in the order of 1 or 2 millikelvins in air without complicated electronic systems. So what's the catch? Well, if we want to use it for wearable devices or textiles, we need to have a polymer that's very stable and reliable. However, as I showed you before, the pectin molecule is very large, very complicated. It's inconsistent from batch to batch. So depending whether it comes from apples, bananas, or mangoes, the molecule is different. It's very hard to calibrate. It's very complex and brittle. So we thought that in order to create materials for wearable, we had to think about material science like we think pharmacology. So let me show you an example that you see on these slides. Perhaps you're more familiar with this than with pectin. If you think about it, humans have been chewing on leaves of the willow tree for over 10,000 years. It was known that chewing on the leaves of a tree, this particular tree, was good for example, for reducing fever, inflammations, headaches, and it has all around medicinal properties. It took Fast forward a few thousand years to discover that the molecule responsible for these properties in the willow tree was this acetylsalicylic acid, which turns out is the key component in something we use on a regular basis, aspirin, which we can now produce synthetically in large quantities and batches. We wanted to do the same. We discovered that pectin had those fundamental properties, but pectin is very inconsistent. So we said, why don't we just reproduce the fundamental motifs of the pectin molecules in order to create a synthetic polymer that could be used in engineering system? So we created a biomimicking solution, a new material showed in red, which is a synthetic polymer consisting of a block ABA. It's a block copolymer with an ABA architecture, which is very cost-effective, can be produced in large batches, and has a giant temperature response and great accuracy that, in fact, even surpasses the one we had measured in pectin. You see the pectin in black, and red is the new material. If you compare this response of the new material with all of the thermal sensors available today, that includes organic, inorganic, and even oxide. Vanadium dioxide is the most important element in infrared cameras and IR detectors today. You see that the response of the new material surpasses them all by at least an order of magnitude. Compared to the industry standard, which is the platinum thermometer, our sensor is 100 times more responsive and 3 times more accurate. Why is this important? Because being so sensitive allows us to reduce the complexity of electronic systems. So in collaboration with the Army Research Office and a local company, Chromologic, we're working to create wearables to fight heat-related injuries and thermal work strains, for example, during training or operations in extreme climate from soldiers. The temperature gradient that we can measure through using 2 pairs of sensors embedded in a simple device allows us to extract the temperature of the inner organs of the body following the laws of heat diffusion. Calculating the differences between this readout and 4 pieces of synthetic material, we can extract the value of the body core temperature and correlate, for example, fatigue and metabolic activities of the users. We built prototypes of these, which are now still too large, and tested them on simulated bodies to capture the temperature response. In this case, the 37 degrees Celsius is the body core temperature of reference, and identified the fact that the sensors work very well when covered by a piece of clothing, which insulate the sensor from the environment, but work particularly much better when the simulated skin thickness is below about 8 millimeters or so. So there is still space to improve the performance, but we're getting close to having at least a workable prototype. We've also developed smart threads that use the new polymer as a sensing element, coating silk fibers with the block copolymer and insulating the fibers with a water-repelling layer. Having smart threads as opposed to flakes or plates allows us to embed these functionalities in electronic textiles using conventional manufacturing methods. The next example I would like to talk to you about, it's a bit of a change in pace and topic. This is a material that we designed to improve the way we interact with machines and communicate with them. Wearable technologies, in addition to being useful for medical devices, like in the example I showed you before, is poised to change the way in which we interact with electronic devices. We already have excellent ways today to interface with computers using visuals, for example, screens, right, and audio. Haptic feedback or tactile feedback is the most significant sensory interface that follows visual cues. It's perhaps the most primordial of our senses in the way we navigate the world. You're all familiar with one example of haptic feedbacks. Your cell phone. A vibration in your pocket is communicating to you very clearly that a phone call is coming or that a message is coming. Now, imagine embedding such functionalities or such tactile cues in a wearable sleeve or a wristband. Encoding different tactile sensations like a tickle, a pinch, or a poke could encode multiple messages like driving directions or personal caller IDs, or even pre-encoded messages like come home, it's time to make dinner, in order to allow us to communicate with one another without having to stare at the screen. We have developed a prototype material that uses different resonance structures, like what you see in these movies, that are simple coils that vibrate at different frequencies. We can control with this vibration both spatial and perceptual sensations that can be designed onto flexible substrates, like imagine very thin polymeric layers, that can produce complex tactile patterns on the human skins on a wide range of frequencies. We call these materials metasurfaces. These surfaces are composed of tactile pixels that can locally amplify both the input displacement of these vibrations and the force. And each of these pixels encodes various deformation patterns. So what I mean, and you see snapshots in this video, is that some of those coils can vibrate up and down, other can tilt left and right, and other can shear horizontally. And each one of these motion encodes a different sensation upon contact with the skin. We studied this mechanically, but we also corroborated the work by user studies conducted on volunteers to open new avenues for wearable and robotic interfaces and communications. Developing such thin and flexible surfaces that function as tactile communication system is important not just for communicating with one another, but also for robotic prosthesis, augmenting virtual and cross realities, and haptic communications. For example, adding a haptic feedback in a prosthesis has been shown to improve the acceptance among amputees, and it's also expected to significantly improve immersive experiences in virtual and augmented realities. The last example I want to show you is yet another change in direction with respect to ideas that allow us to explore new functionalities and applications for advanced materials in wearables. I'm sure you all remember the cool properties of the bat suit. If you don't, let me remind you. The bat suit is fashionable. It's technical, it flows, it comfortably drapes around the body of Batman and softly flows when he moves. But yet in moments of need, it allows Batman to fly, and it allows Batman to protect himself. In fact, it stiffens on command, like you see from this snapshot from the comic, to function as a bulletproof vest. This next project that I'm going to be discussing with you about is going to get us closer to these applications. But first, let me go back to one of these discoveries I introduced at the beginning. The earliest form of metal armor that was worn by the average soldier during the medieval times was the medieval chainmail, like the pictures depicted here. It was a flexible armor which was made from interlinked metal rings. It provided protections against being cut, for example, or sharp points, and blades in general, but it was rather ineffective, if you think about it, against heavy blows from a blunt weapon. But the resulting structure that was actually very useful in combat was particularly liked across the world because it could bend, fold, and drape comfortably over curved objects and the bodies of the wearer. Now, unlike other fabrics, the ones you may be thinking about, which are woven or knitted into continuous materials like fibers, threads, or wires, the basic building blocks of the chainmail armors are discrete. They're just like granular particles. And when I think about granular particles, you can think about something very familiar to you, again, borrowing from the kitchen, like coffee or rice. Assemblies of such granular particles are known to undergo a particular change in their mechanical properties that's been studied extensively in the physics realm called jamming. Jamming is a phase transition in materials that does not rely on temperature changes like in ordinary materials. Think about water melting or solidifying through ice, but is instead controlled by geometric constraints in the granular matter. Now, if you think about coffee, for example, when you buy coffee, it usually comes in these vacuum-packed packages, which is actually very stiff. It's almost like a brick. But when you open the package, you can pour the coffee like a fluid into and in fact, it takes the shape of the container where it is poured. Now, one special properties of coffee, grains, rice, or nuts is that they only react, these particles only react in contact by repulsive interactions. And hence, this response of rigidity that you can feel when you buy vacuum-packed coffee is generally only performing well in compression, not so much in tension or bending. So we decided to 3D print special forms of chainmail armors that are consisting of complex particles. This would be the equivalent of a coffee grain or a ring in a medieval chainmail that can take different shapes and sizes, can be topologically interlinked or locked, and can form sheets with interlocked particles. This is a new type of architected fabric that consists of complicated geometries that can be promising candidates because it can use this tunability of the stiffness of coffee in order to create smart wearable that adjust their stiffness on command. The advantage is that we have cohesive interaction through interlocking, and because the particles are hollow and three-dimensional, they have more empty spaces, which means they can reduce the density, making the material more lightweight and less dense. The key here is to design the complexity of these particles to induce having more contacts between elements next to one another. So we 3D printed these chainmails. These are some sheets of examples that started from an octahedral particle. We then explored many more geometries that have a very low density, only 20% of material volume occupation, and they can drape and fold around the body very conveniently. What is interesting of these fabrics, though, is that if you look at this video that's going to start playing in a moment, this is going to be a numerical simulations of 2 layers of these chainmails that are responding to a boundary stress. What it means is that we effectively compress them together as if you think about vacuum packaging coffee. So what happens in this case, the particles jump together and effectively transition these wearables from a soft, unjammed state that is very soft and drapable to a stiff and jammed state, that it's capable of supporting loads, rather large loads, and becomes very stiff and can even protect from sudden impact. Turns out that one thing that's interesting is that if we just tested the bending stiffness, which is convenient as a measurement for clothing, by fixing 2 ends of these chainmails and just applying a force in the middle, we can see that by increasing this boundary pressure to jam the particles together, you can see that the stiffness, or that is the response to the load that the material can provide, increases dramatically when the particles are interlocked. But if the same particles are not interlocked, like coffee grains, this response of stiffening is much reduced. So it's not as effective as in the case of compressing only particles. This tells us that this particular locking mechanism is suitable, for example, for wearable systems that can jam with external loading. We have explored a number of geometries and different particle shapes to evaluate the different locking patterns and evaluate which among those are more suitable for stiffening behaviors. And another feature of these studied fabrics is that they can be shaped into different geometries before being jammed. For example, into load-bearing structures. To demonstrate this, we manually configured these sheets into a table or an arch, and then we apply the confining pressure that, in this particular case, is effectively done similarly to the coffee example by using a Ziploc bag around this particle and vacuuming out air, so applying negative pressure. The resulting structures that are jammed remain mechanically stiff and are able to bear loads that is up to 30 times the weight of the structures themselves. And they can be reconfigured over and over, so jammed and unjammed and reused for different systems. And we're now exploring the use of the systems, for example, for casts and exoskeletons in medical devices. But possible applications of these systems really depend on the scales. And because the jamming transition is something that is not specific to a particular scale, but it can be valid when the particles are very small or very large, we can think about different length scale applications ranging from the medical supports that I mentioned before, all the way to reconfigurable architectures like at large scale and large stiffness moduli, which could be used for deployable emergency shelters, bridges, or temporary installations, for example, after natural disasters, until more permanent structures can be put in place. We're also focusing on different materials. And so these the two images you see here allows us to demonstrate the fact that these kinds of architectures can be produced with different technologies, with different manufacturing approaches, using different materials. On the left, you have nylon, which is, again, suitable for wearables. On the right is aluminum, for example, for stiffer supports. With the integration of alternative methods for confinement, which is not necessarily vacuum pressure, we're now exploring, for example, programming stiffness in the fabric through additional methods like electrical, magnetic, or thermal controls. And we hope that such interfaces could also be used, for example, in other areas. We're working now with fashion designers to integrate materials in true wearables, creating, for example, 3D chainmail-based shirts and gloves. But we're also designing self-stiffening supports, like the one you see on this video, which see if we can play, oh, here we go. Which, for example, could be used as a neck support that can self-stiffen as needed, but allows breathability, comfort, and more wearability in its lightweight architecture by using these coiled systems that can jam by simple torsion. This, though, brings me to a close. And I hope I've given you 3 examples of new materials that can be embedded in wearables. But these are just 3 simple examples that are currently pursued in our lab. There is a wealth of other activities that are pursued in other academic and industrial institutions that are expanding the wearable frontiers much beyond what you've seen today. Other labs, even here at Caltech, for example, are already showing that materials can detect diseases from sweat or continuously monitor internal organs via ultrasounds, improve rehabilitation of patients, and monitor chronic diseases. New materials for wearable, paired with advances in computing and manufacturing, which make these advances possible, will continue to permeate our everyday life. The future of fashion will not only be beautiful and functional, but will also help us stay healthy, communicate, and adaptively support our everyday needs. And I hope everybody will welcome these advances and discoveries in the future. And I shall be remiss if I don't acknowledge the people that really made all of this possible. First and foremost, all the graduate students, postdocs, undergraduate students, and staff scientists in the group that have worked on these subjects and others that I didn't have the time to describe today throughout the years. And of course, the funding that have, over the course of the years, supported parts of the projects that I described today. And from here, I would be very happy to take any questions you may have. Thank you for attending.
Hello. First of all, congratulations on the great presentation. A question from the audience is there any way 3D printing and pectin temperature sensing could be combined?
All right, thank you for the question. And there is, in fact, a way to combine the 2 methods. We have explored, or maybe I should say skimmed the very surface of these, but trying to 3D print on surfaces different pixels of pectin in this case in order to create temperature mapping devices. But I think we've only really covered a very preliminary work in this space. And I think there are certainly promising opportunities in combining some of the functionalities I showed today. Just imagine the self-stiffening armor also being capable of monitoring, for example, soldiers' metabolic activity and heat-related injuries. There is a lot that can be done in this space, and we're just at the very beginning. Yep, question?
Buonasera, grazie.
Buonasera.
Just to give you a little bit of a context, I am an Art Center alumna, and subsequently I taught entrepreneurship at Art Center. I also worked for the Sovereign Wealth Fund of New Zealand, because I'm also a banker. And what I noticed is that New Zealand does a fantastic job commercializing materials and building companies around that. How can we contact, as Art Center alumni and entrepreneurs, how can we get in touch with Caltech to scale these amazing innovations so they don't stay theoretical forever?
So first of all, thank you for coming tonight, and thanks for the comment. We love to work with the Art Center. We've had, in fact, a really recent collaboration, and as I showed before, we are trying to expand these collaborations even to fashion designers on the other coasts, where we're trying to really explore how can we integrate these materials in true wearables, not just in the lab, and what are the needs that fashion designers, users, manufacturing industry, and so on require us to fulfill, because otherwise we tend to ask very specific questions in the scientific domain, but we don't know how those questions really translate to scalability. And I think, I don't know that I can answer for Caltech and large, but I can certainly answer for what concerns my group. I'd love to talk later, or if you have contacts that we should pursue or suggestions for this space, please follow up with me after the talk, and we can certainly explore this. We're always looking for such collaborations.
I would love to continue the conversation because I feel like Silicon Valley kind of steals, Southern California's thunder, and what you guys have is incredible.
Thank you. Yep.
I'd like to ask a question, and this regards the jammed and unjammed materials technology. And I'm curious as to if you've measured the effect of strain stresses upon both the jammed and the unjammed technologies. And if you have, could you elaborate on that?
Oh boy, we did. But I was told that I had to remain very general for the audience. so let me see if I can even show you one. Maybe I can show you one of the slides I particularly love. So first of all, yes, and the stress and strain relationship between this jamming transition, first of all, depends very much on the particle geometry, and has also not just the particle geometry, but also how the particles are linked with one another. So you can take, for example, ring particles and connect in multiple configurations. And so that will affect how much stresses and strains the material is able to support with different loading conditions, whether you shear it, bend it, pull it, compress it, and so on. But one thing that we found particularly exciting is that no matter what the geometry we used was, for example, whether they were octahedron or interconnecting rings or cubes or rhombohedrons, we found that the mechanical response, which is actually the stiffness, which is what relates the strain and the stress, and the way these particles get into contact would all collapse into the same scaling law. Now, why this is exciting is that it allows us to have tools to design this system in a universal sense, but it also tells us which ones of these geometries functions better in terms of stiffening. And I'm just going to point to one thing, which is, if you look at the rings are the medieval rings. Actually, there are some medieval armors that were using even these squared functions. these symbols, they're the circle and the green square, are way up here, which means that these geometries are incredibly effective at stiffening when you compress them. So their stress-strain response happens to be more tunable than any of the other geometries. This is because these materials densify very easily because they're two-dimensional rather than three-dimensional. So while the stress-strain response is optimal in a sense of stiffening, they also become heavier. So we need to think about the trade-off between the stress-strain responses and the wearability and the comfort. But thank you for the question.
Thank you so much.
Yep.
Hi, how's it going? Mike Shaw, nice to meet you. Had a question about the compression, unjammed and jammed material that you were talking about. So if you lose a link in the chain, how does that propagate? Or does that propagate across the material? Is it localized? And how does this affect when you have it under load?
Okay, so the beauty of this material is that it is ultimately discrete. So while, for example, when you're wearing clothing and you pull a thread, and then if you keep pulling the thread, you're left without clothing. In this particular case, if you just break one or a few of these linkages, what happens is that individual particles may fall off. And so I think the integrity of these sheets remains in place for a longer time than regular clothing that is basically a single thread continuously woven usually allows or gives in terms of stability. Now, it depends, though, on the material you use, because you may be using polymers or metals, and the responses may be different in the two cases. And it also depends on the loading. Some of the things I didn't have the time to show is that we've been working with the Army Research Office to see if some of these chainmail systems could really work like a bat suit, meaning once they're stiffened, can they block, for example, loads that are more similar to mechanical loads at high velocities that may be of interest for defense applications. And it turns out that in those specific cases, the fracture is a bit more problematic because the particles at high speeds can fragment, and that's not a desirable outcome. But for wearables, they're definitely more resilient than continuous threads.
Thank you very much, appreciate it.
I was wondering how the clothing for the 3D printed chainmail would be made comfortable.
Oh, I love this. So actually, that is a big problem, because right now, thank you for asking that, because right now, if you try, and we have a lot of these samples in the lab. I should have brought a few so you could try and feel it. They tend to be rather scratchy. So when you wear them, they're not, especially these particular geometries, they're not as smooth and as soft as many others. That said, we're working on these, and there are some materials that you can 3D print with, unfortunately at the moment, rather expensive 3D printers, but eventually they'll become more cost effective, that can print very squishy and soft particles. So we hope that in the future we will be able to develop new materials that are more comfortable for wearing. But thank you.
Thank you, too.
If you're using these for apparel, how are you going to avoid creating a lot of pollution if they're not reusable?
Yeah.
Because clothing wears out, and anybody that washes a pair of jeans 4 or 5 times knows that colors fade, everything changes. So that's all.
I hear you. So we haven't gotten that far ahead, because right now we can make rather small patches of materials, but I think there are 2 possible solutions to that in the future. One is we could think about using more sustainable materials. We don't need to use plastics or aluminum, right? We can print these with pretty much any material that could be recyclable polymers. But even in this case, viscose or other materials that are used for clothing today could be, in principle, used to make similar systems. So one solution could be, let's invent new materials that are more sustainable, recyclable, perhaps bio-derived. And actually, turns out we're trying to work on that, but that's a separate story, maybe for the next Watson lecture. But the other part is to think about materials that can be just like the clothing we wear that don't degrade so quickly, right? So we can use it and reuse it and maybe pass it on to, to others, like our kids, pass on to brothers and sisters as they go. And I think in that sense, these kinds of systems would not be so much more polluting or more problematic than the clothes, or many of the clothes and devices and garments we use today. But it is a very important point.
Thank you.
Welcome.
Is the stiffness limited by the stiffness of the material you're making these units with? Is that like a limit? And how about the breaking strength?
Okay, actually this is a very difficult question to answer, but in short, it is related to two separate things. And let me go back to that favorite slide of mine, the scaling law. So there are two things that embed this stiffening behavior. One, it's purely the geometry. And to make it really simple, it's, you look at, so this axis here, it tells you how much it stiffens. So the higher these values, the more the fabric stiffens. Now, it turns out that the more it stiffens, it correlates with the more these particles are in contact with each other. So there is a purely geometrical effect, given the same material overall, that depending on how many points of contact these particles have, whether they are rings that can have surfaces of contacts, or whether they are octahedrons that have contacts in many, many different places. And when I talk about contact, I mean tensile contacts, which means when you pull the rings apart, or also when you compress the rings together. So both are important for stiffening. And that's a purely geometrical problem. And then there is a second effect, which is the material problem. Once you are jamming these particles and they are really in contact, so much so that you're squishing them like pancakes, then the material response really comes into play. So there, it really does matter, for example, if your particles are made of nylon or aluminum or steel, because that will determine at what point these rings break or deform permanently so that they become unusable in the future. So there is an effect that actually comes into play at both scales, the single particle material and the way the particles interact with each other.
Hi, good evening. Thank you for the great talk. I was wondering, have you ever considered combining different shapes, and would that make a difference?
We have been thinking about it, and I think it will make a difference. One of the things that I expect to happen when we combine, for example, particles of different shapes in the same sheets or the same interlinked architecture is that when we jam the material, not only do we stiffen it, but we may change its global shape. So what I mean is that if there are particles that have different shapes, imagine like putting a cube next to one of these intersecting rings and so on, they will probably curve. They will locally kind of jam such a way that the sheet that was originally flat will assume a different geometry. It could become, once you jam it, it could become a dome, or it could become a saddle, or we could engineer it to be shape changing in addition to stiffening. This is an intuition, though, because we haven't yet explored these in details. It's certainly something we want to do in the future. So, good point.
Thank you, and good luck.
Thanks.
To conclude this wonderful presentation and Q&A, the final audience question is, which of these technologies do you think is closest to being ready for consumer manufacturing or larger production?
So I have been famously wrong in these predictions in the past, which is perhaps why I should stick to being an academic. However, I think that at least from where we stand in the lab, I think the temperature sensing materials, the one that I showed you before, it was the very first example. Let me come back to it, for example, in this slide. It's probably the one that's closest to commercialization. Because the polymer can be produced in a scalable fashion already, and we know it to be low cost. We also know to have these useful functionalities that can be embedded in different systems. Today, I decided to focus on wearables because it was the topic of the presentation. But for example, we have been using the same films of these materials to create coatings for wheelchairs or beds, for example, to monitor motility of patients that are that deal with conditions that confine them to lower mobilities. And I think many of those applications are actually very close to being transformative in an industrial sense. There are still some small issues to be resolved, like, for example, cost effectiveness, packaging of the electronic systems, and so on. But there is nothing that is fundamentally, physically impeding us from moving commercially. It's just a question of miniaturization and implementation. Thank you.